Welcome to the first episode in our series on elliptic curves. Today, the goal is not cryptography yet. The goal is to build intuition. What is an elliptic curve? Why do its points form a group? What does scalar multiplication mean? What are torsion points? And what does the j-invariant tell us about the curve itself? A good guiding question for the whole episode is this: how can a geometric curve carry algebra? We will move from equations to geometry to a group law, and finally to arithmetic phenomena like torsion. Formally, an elliptic curve is a smooth, projective algebraic curve of genus 1, equipped with a distinguished point. That definition is correct, but at first it feels heavy. So rather than unpacking every word immediately, we will move to a more concrete picture and return to the geometry only when it becomes useful. For this first encounter, you can think of an elliptic curve as the set of points satisfying a cubic equation, together with one extra point at infinity. That picture already contains most of the intuition we need. Consider the curve y squared equals x cubed minus x plus 1. Every real solution of this equation appears as a point in the plane. Since y appears squared, many x values produce 2 points, one above and one below the horizontal axis. That simple symmetry will later explain why inverses look so natural on an elliptic curve. An elliptic curve can be written in several useful coordinate systems. The most common for theory is the Weierstrass model. Montgomery and Twisted Edwards models often make particular computations more convenient. The equation changes, but the underlying curve may remain the same after a change of coordinates. One invariant that helps organize elliptic curves is the j-invariant. For a short Weierstrass equation in characteristic different from 2 and 3, it is given by this expression. Two elliptic curves over an algebraic closure are isomorphic exactly when they have the same j-invariant. So j is a compact fingerprint of the underlying curve, rather than of one particular equation. The values 0 and 1728 are especially important because they often signal extra symmetry. The j-invariant will return later, whenever we need to compare or identify elliptic curves. We only need one quick fact about smoothness. A smooth cubic has no cusp and no self-intersection. In short Weierstrass form, this is exactly the condition that the discriminant is non-zero. That is what keeps the group law geometry well behaved. Projectivizing the equation adds one more point, the point at infinity, usually written O. It is built into the curve's geometry and becomes the identity element of the group law. Now for the remarkable part. The points of an elliptic curve can be added. To add P and Q, draw the line through them. A line intersects a cubic in 3 points, counting multiplicity. Call the third intersection S. Then reflect S across the x-axis. The reflected point is P plus Q. Here P is 0, 1, and Q is 1, 1. The secant is horizontal, the third intersection is minus 1, 1, and after reflection, the sum is minus 1, minus 1. This addition law satisfies the group axioms. The sum stays on the curve, the point at infinity is the identity, reflecting a point gives its inverse, and addition is associative. Associativity is not obvious from the picture, but it is what turns the geometric construction into genuine algebra. To add a point to itself, replace the secant by the tangent line. The tangent touches the curve at P, meets it again at S, and after reflection gives 2p. In this example, the tangent slope comes directly from implicit differentiation. The doubled point is 1/4, minus 7/8. Even this simple geometric rule quickly produces non-trivial arithmetic. Repeated addition leads to scalar multiplication. Bracket NP means adding p to itself n times. This operation is the engine behind elliptic curve arithmetic. Computing NP naively would be slow, but binary expansion makes it efficient. For example, 13p becomes 8p plus 4p plus p. So the geometry scales into practical arithmetic. Some points eventually return to the identity after repeated addition. These are torsion points. More precisely, P is an n torsion point when bracket NP equals O. All points killed by bracket n form the subgroup E of n. Over an algebraic closure, when n is coprime to the characteristic, the n torsion has a clean two-dimensional structure. It looks like two copies of the integers modulo n. Consequently, there are n-squared n torsion points. Let us compress the episode into one picture. An equation defines a curve. The curve carries a group law. Repeated addition gives scalar multiplication, and finite order behavior gives torsion. Alongside that arithmetic, the j-invariant helps identify the underlying elliptic curve up to isomorphism. Before we finish, there is one essential bridge to the rest of the series. Over a finite field, coordinates are computed modulo q, so the curve has only finitely many points. Those points still form an abelian group under the same algebraic addition law. This finite setting is where the later cryptographic constructions live. In the next episode, we will introduce isogenies, structure-preserving maps between elliptic curves. Thanks for watching.